Stanford researchers just proved that AI can design 16 working viruses from nothing but DNA sequences, not theoretical designs, functional ones that replicate in cells. The unsettling part: the same large language models powering legitimate research are answering the same prompts without flagging them. The infrastructure is already in place. The bottleneck isn't expertise anymore, it's intent, and intent is invisible. And Stanford researchers just proved it works in practice. They fed large language models DNA sequences, plain text, nothing fancy, and asked the models to generate instructions for assembling viruses. The LLMs didn't hesitate. They didn't flag the request as dangerous. They generated 16 functional viral sequences that actually replicate in cells, not theoretical outputs, not designs that fail when you try to build them. Working viruses. This matters because it destroys the argument that's dominated biosecurity discussions for 2 years, that AI is just pattern matching, sophisticated autocomplete, incapable of causing real material harm. The Stanford researchers, according to their own published work documented in the Council on Strategic Risks Assessment, showed that language models can output instructions that translate directly into biological function. The models generated sequences without any special prompting, without jailbreaks, without elaborate social engineering. They just answered the question. But here's the real shift. These weren't variants of known pathogens that the models memorized from training data. This represents the convergence of two capabilities that were previously separated: AI's ability to design novel biological sequences and biology tools' ability to synthesize them into actual organisms. That convergence collapses the traditional bottleneck for bioweapon development. It used to require a PhD in virology, years in a biosafety lab, institutional access. Now the bottleneck is internet access and a willingness to ask the right question. And that's where the real infrastructure fails. A functioning DIY bacterial gene engineering CRISPR kit, the actual tool you need to build what an AI just designed for you, costs $85. $85. You can order it online. It ships to your door. For context, that's less than a new video game. It's cheaper than 3 months of Netflix. These kits exist for legitimate reasons. Universities use them. High schoolers use them in science competitions. Biotech startups prototype in garages with them. The democratization of genetic engineering was supposed to be a good thing. It lowered barriers to innovation, spread scientific literacy, made biology accessible beyond million-dollar university labs. But democratization cuts both ways. The same accessibility that lets a teenager in Ohio run protein experiments in her bedroom also lets someone with zero formal training and zero legitimate intent do exactly the same thing. The bottleneck isn't knowledge anymore. It isn't equipment. It's intent, and intent is invisible. The screening infrastructure doesn't exist. Most commercial DNA synthesis labs, the places where you'd actually order the genetic sequences an AI designed, only some have committed to checking for misuse potential. There's no unified standard, no registry, no way to know if the person ordering a viral genome sequence is a researcher at Stanford or someone following an internet guide in a basement somewhere. And that's exactly what's starting to happen. The real danger isn't any single AI tool sitting in isolation. It's the integration of them into a unified pipeline where one system talks to the next without human intervention in between. Consider what's now technically possible. Protein design tools can generate novel toxins with enhanced stability, compounds that existing antidotes won't recognize or neutralize. According to the Council on Strategic Risks, these tools are already mapping the entire misuse risk chain. Simultaneously, genome assembly tools can stitch together viral genomes designed to slip past current nucleic acid synthesis screening. That last human checkpoint supposed to catch dangerous orders before they ship. The pieces were always there. Now they're connecting. A company has already announced the first LLM chatbot interface that controls a suite of biological design tools. Not in 5 years. Now, think through what that means operationally. Someone without computer science skills, without formal biology training, can open a chat window and describe what they want. A more stable version of a known pathogen, or something novel entirely. The AI chains the entire process together in one conversation. Design the protein, model the genome, generate synthesis instructions, output the DNA sequence ready to order. No translation layer, no expert in the loop, no friction. The person ordering that sequence from a synthesis company looks identical to the Stanford researcher. The screening systems can't tell the difference because they're looking at the same genetic code. What changed is who can now generate that code, and how quickly they can do it, that compression of the design-build-test cycle. The thing that historically required a laboratory, years of training, and institutional oversight, that's the convergence problem nobody's ready to regulate. And here's where the expert disagreement starts to fracture the entire conversation. Ask a room of biosecurity researchers when AI becomes a critical threat to bioweapon design, and you'll get answers separated by decades. Some credible voices argue that current language models remain fundamentally marginal for actual bioweapon production. According to Kathleen Vogel, AI systems work with codified data, sequences, structures, published protocols, but they cannot evaluate the tacit knowledge that has historically protected against proliferation, the embodied know-how of former bioweapons programs, the judgment calls about what works in practice versus what looks good on paper, the intuition about failure modes. AI doesn't capture any of that. So even if an LLM spits out instructions, a non-expert trying to follow them still hits a wall of practical constraints that no amount of language understanding can dissolve. But other experts see a threshold effect coming. Brand researchers and AI safety teams warn that as foundation models improve in reasoning and planning, there's a point where the system stops needing human intermediaries, where the AI can autonomously design novel bioweapons, simulate their behavior, iterate on failures. Not in 2025, maybe not in 2027, but the trajectory is real. And the moment it tips could feel like it happened overnight. The catastrophic part is nobody knows which timeline is correct. And the cost of guessing wrong is not an academic paper that ages poorly. It's biological. Regulation, meanwhile, remains scattered across 3 separate domains. LLM providers have their own safety guidelines. DNA synthesis companies screen sequences, some of them inconsistently. Biodesign tool developers operate without unified standards. No single authority has jurisdiction over the entire chain. And that jurisdictional gap is the core reason regulation is losing. Agencies like the FDA, USDA, and NIH each control fragments of the biosecurity chain, but none of them owns the AI layer that ties it all together. The Council on Strategic Risks documented this clearly. Biological design tools are proliferating across protein design, genome assembly, and pathogen simulation, but no single regulator has authority over all 3, let alone over the language models feeding them. 1. Here's the deeper problem. The same AI systems enabling breakthrough vaccine design and therapeutic discovery can be repurposed for weaponization in minutes. The code doesn't change. Only intent changes. A language model trained to help Stanford researchers design safer proteins has no ability to distinguish between that purpose and helping someone design a weaponized toxin. It's the same weights, the same outputs, the same dual-use surface. Commercial DNA synthesis labs, the actual gates that could stop weaponized sequences from being built, only some have committed to screening for misuse too. That means the safety checkpoint is optional. A determined actor can shop around. Then there's the agreement problem. Surveys show less than 56% of NLP researchers can even agree on what dual-use risk means, and the ones who do think the definition is too vague to enforce. You can't regulate what you can't define. By the time regulation catches up, the AI will have evolved 3 times over. The lag isn't incidental, it's structural. Because the missing ingredient was always human, tacit knowledge, the stuff that doesn't live in papers. You can read every published study on weaponized pathogens, every formula, every sequence. What you won't know is how temperature affects stability in the 3rd week, which strains fail under stress, where the supply chains actually run, how to avoid contamination when you're working in a basement. That's the knowledge you get by doing it, by failing, by watching someone else fail, by having your hands in it. AI systems can't evaluate those tacit dimensions because they can't be codified into text or data. According to Kathleen Vogel at Centrum Balticum, they work with what can be quantified or made explicit. They're blind to the embodied part of bioweapons work, the part that has historically protected us. That's the current firewall. The problem is it's eroding in real time. As AI becomes more capable and gains access to more experimental feedback loops, as biological design tools start talking to language models, that gap closes. Some researchers think we're decades from crossing that threshold. Others think we're years away. Nobody knows which is right. That's what keeps biosecurity experts awake. Because the question now is whether we're watching a slow-motion disaster or a sprint toward one. The Stanford viruses weren't the smoking gun. They were the warning shot nobody wanted to hear. NeuralWire. Researchers generated 16 functional sequences, proved the principle, then published it. That's how science works. That's also how you hand the blueprint to everyone paying attention. Here's where the fracture runs deepest. Some experts say this is a solve-it-now problem. Lock down the large language models. Restrict access to biological design tools. Impose unified screening across every DNA synthesis lab on the planet. The problem with that option, it kills the legitimate research. The vaccine designers, the cancer researchers, the people building the next generation of medicine. You don't get to save both. The other option is to wait. Watch the capability curve. Adapt as the threat materializes. By then, you're no longer preventing anything. You're responding to it. You're managing the damage after the code runs. Right now, we're doing neither of those things. We're arguing about which question is even worth asking. That's not a strategy. That's a confession that nobody knows what happens next. The Stanford researchers didn't design those 16 viruses to scare us. They did it to prove a point. The guardrails we thought were in place don't exist. AI can design bioweapons. The tools to build them cost $85. And nobody's actually agreed on how to stop it. If you want to understand what's actually happening in AI safety beyond the hype, subscribe. We're covering the real risks nobody's talking about. Next video drops Tuesday.